you can take a compound and break it down into its elements by some sort of chemical reaction. And you can take elements and build them up into compounds by some sort of chemical reaction. So chem, RXN. Chemical reaction to break them down, chemical reaction to build them up. Okay. The other thing this says is that you need to have 2 or more atoms of different elements bonded together to make officially a compound. Remember those 7 diatomic elements? Okay, the Hofburnickel, Hofburnickel, okay? Those are not compounds because they are 2 atoms of the same element joined together. So this movie didn't play at my office, so I'll just describe what this movie would do. You guys know in lab on Thursday, what you guys did was take regular old magnesium and connect up an oxygen atom for each magnesium atom and make magnesium oxide. What this actually would have done was to show you how you can take mercury, I think it's mercury 2 oxide, okay, and break it down by heating it to give you mercury solid and or mercury liquid and oxygen. So this emphasizes this breaking down to get your elements back from a compound, such as mercury 2 oxide. So we use chemical formulas to say what atoms are joined together chemically with chemical bonds in a compound. So here's some common chemical formulas for some compounds. One of the things you need to be able to do, and I bet you all can do it, is to recognize, for instance, down here, when we have either one of these, actually, the fact that we have 2 outside brackets NH4 means that we have 2 NH4 groups. So actually some of your homework, but I think we'll get to the homework slide today. Some of your homework requires that you recognize, can you see that there are, what, 8 hydrogens, 2 nitrogens, and 1 sulfur, and 1 repeating unit of that. Down here with the magnesium nitrate, we have 1 magnesium, 2 nitrogens, and 6 oxygens. Okay. Usually works pretty well. So there is a distinction between 2 broad types of compounds. There are molecular compounds and ionic compounds. So molecular CPD is my abbreviation for compounds, and ionic compounds. And that is not any small, that's a pretty big distinction. When we start to talk about compounds, I like to kind of come up with the differences. And so this tally, if you have a place in your notes that you want to refer to, come back to this tally, you can. So molecular CPD on the left and ionic CPD on the right. Okay. So one of the things actually we can go ahead and differentiation we can go ahead and put up is that molecular compounds exist as molecules. I'll say 1 unit is equal to a molecule. And over here for ionic compounds, 1 unit is equal to a formula unit. Okay. Formula unit, abbreviated, of course. I'm sorry, but it really is FU. I'm just saying, I didn't make that up. Okay. What makes these different, actually, is how the atoms chemically bond together. So these are all examples of molecular compounds. And they have a nice, it's kind of like when you go to see a magician and he puts his assistant on a table and he tricks your eyes into thinking he can take his hand and go all the way around the assistant and nothing's holding her up, okay? That's what molecules are like. You can put your hand all the way around and nothing is like connected to it per se. Okay. This is just acetone. So the formula for acetone is 2 carbons, 4 hydrogens, and 2 oxygens. Of course, the black are the carbons over here. The white are the hydrogens and the red are the oxygens. Acetone, we're going to talk about different formulas. So to me, like the real formula is C2H4O2. We can break that down, as some of you maybe know. We can divide everything by 2, and we get a more reduced formula called an empirical formula. So instead of 2 carbons, it's 1. Instead of 4 hydrogens, it's 2. Instead of 2 oxygens, it's 1. That's the empirical formula. We'll be talking more about that. But this is, if we wanted to look at kind of unpack acetone, this is what acetone looks like. We don't do a whole lot with it in Chem 1, but more in Chem 2, talking about functional groups. Okay, so cool thing about acetone is it has that alcohol functional group, and it has this double bond oxygen functional group. And this is just another kind of it's like your ball and stick, but it's a space filling model. Yeah. So a molecular compound, you talk about them in terms of a molecule. I'm going to contrast that with ionic compounds here in a minute, but like for instance, for a water molecule, you know which oxygen goes with which 2 hydrogens. You know that. Okay, it's a little family unit. Not so much with ionic compounds. So I don't think these will play, but I'll try them. So I'll just describe to you what that would do. Over here I have something to add to our list of compare and contrast. So with regard to molecular compounds, I'll say example EX, for example, H2O. An example of an ionic compound is the stuff you put on your food. Table salt is NaCl. So table salt basically has 1 Na, 1 sodium, and 1 chlorine, okay, running around. We call that repeating unit a formula unit. We call an H2O repeating unit a molecule. Okay. So what this would have done, if it chose to animate, okay, is, and we'll be talking more about this, but just to kind of give you an introduction, here we have a neutral sodium atom and a neutral chlorine atom minding their own business. Okay, they're neutral. They have the same number of protons as electrons. Protons in the nucleus as electrons in the cloud outside. So one of the things about sodium, all 1A elements tend to want to kick off 1 electron. They just want to. But you get a rare gas, what we call a rare gas configuration. So kind of stepwise, I'm going to show 1 electron going from the sodium to the chlorine. Well, what that does then is it leaves behind a sodium cation, an Na+1, and a chloride anion, a Cl-1. This is just kind of a little story that happens with your table salt. And then what happens is just like kind of, unlike charges attract, that's exactly what happens. Basically, we have the sodium and the chlorine, and if I make this blue line my chemical bond, that dot, dot, dot right there is an ionic chemical bond. Exactly. Smile faces all around. So that's kind of a step process that happens for ionic compounds to form. Ionic compounds have ionic chemical bonds. It's a beautiful story. So again with the salt, the thing about salts, or excuse me, the thing about ionic compounds, and I'm going to go ahead and put this over here. Ionic compounds tend to form crystalline lattice structures. They form crystalline lattice structures. Okay, and can you almost see, so kind of from left to right, left is the photo, but the right one actually is what's happening on the atomic level. Okay, you can see these gray bars right there would be the ionic chemical bonds that's formed between a cation and an anion. Okay? And the thing about it is it's really hard to say where one unit begins and the other unit ends. So, for instance, if to get one repeating unit of this, I go in here and I get that yellow one and that white one. Okay? But also, that yellow one is bonded to this white one over here. And it's also bonded to this one up here. Okay? In this sort of structure, it's got like 6 options. Well, I have 6 colors. Okay? But, yeah. So actually we say instead of being kind of like a family, it's more of a community. It's like networked. Okay? So we call an isolated repeating unit a formula unit instead of a molecule. See how like the magician couldn't take his or her hand and go around? See, it's connected to other stuff. Okay? So this just pretty much says and is of what I was explaining and what the figures showed. Okay? You pick any one cation or anion, and in the examples we looked at, they basically have 6 options. So something else to go ahead and write up over here in the compare and contrast. It's helpful at times for you to look at a formula of a substance, to look at a compound's formula and to say, is that a molecular compound or is that an ionic compound? It makes a difference. It's a player. Which one is it? Well, here are some rules on how to do that. Metals bonded with nonmetals. Now, here's where you need to remember the discussion from Friday, where we put a JAG in the periodic table and we separated nonmetals from metals. Okay? So basically, if you have one of each joined together, okay, then you're talking about an ionic bond there. So you have an ionic compound. Metals bonded with nonmetals produced ionic compounds. So under ionic compounds, we could put metal plus nonmetal. I wonder if this is the bad one. That's the good one. Maybe they're both bad now. So here's where I tell students, don't be shy in your periodic table and trying to find an element of interest. So for instance, sodium, you're like, table salt, that's so not metallic. Well, if you find sodium on the periodic table, it's clearly 1A, it's definitely a metal. So sodium's your metal, chlorine is your nonmetal, okay? So it falls under this. Now this works about maybe 98% of the time. Okay. Nonmetals bonded with other nonmetals will give you molecular compounds. So nonmetal bonded to a nonmetal. Now, if you're one of these that is kind of keeping track of the possibilities, the one possibility I didn't say is a metal to a metal. And if you're kind of familiar, which I'm not real familiar with, like stainless steel, these different metal alloys, okay, definitely you have a chunk of metal that has, zinc, aluminum, all sorts of different metals frozen in it. I will say that actually it's like a solid solution. There's no chemical bonds per se in there. There's intermolecular bonds because it's frozen, okay, but there's no chemical bonds. Metals don't bond to other metals to make compounds. They just don't. Every time I say that each semester, I'm like, now, do they? And I'm trying to think of an example. No, they don't. Okay? Nonmetals and nonmetals bond. Okay? Nonmetals and metals bond. So that's your hint. So I was noticing today, and I've mentioned this before, anytime you see AMUs, you guys are going to have to make the transference to U's because I'm old-timey. I'm working on it. But we said that a really small weight is an AMU, and we use it to describe how heavy atoms are, right? That decimal number is how heavy an atom is in AMUs, right? So students really usually don't struggle with this idea, and you've seen it before. How do you say how big a water molecule is? How massive a water molecule is? Well, you take the mass of 2 hydrogens, the mass of oxygen. That's it. We would call that the molecular weight of water, okay? So it's not too bad. You definitely need a periodic table, and you'll definitely have a periodic table on all your exams in here, okay? You should collect them. So average atomic weight, molecular weight, average atomic molecular weight. It's the same thing, molecular mass. Now, the only difference between the previous slide and this slide, molecular weight and formula weight, just has to do with the compound you're trying to get a fix on how much it weighs. If the compound is an ionic compound, then honestly, if it's an ionic compound, we can't talk about molecular weight, okay? If it's an ionic compound, we have to talk about formula weight. If it's a molecular compound, we talk about molecular weight. So in other words, if we were going for the mass of an NaCl, that would be formula weight. If we were going for the mass of an H2O, that would be a molecular weight. I think sometimes that what I've seen kind of just in pop chemistry is that I think this is kind of almost a lost art, you know, a little bit. Okay, so let's do a few examples. Hydrazine. The formula is N2H4. Oh, one more thing to add over here. Hydrogen, do you guys remember how hydrogen on my periodic tables is 2 places? Well, this is kind of why it's on 2 places, I would say. Hydrogen, usually you can consider a nonmetal, okay? Hydrogen is usually a nonmetal. So actually, I'm going to put that little comment under molecular compounds, okay? Hydrogen, usually a nonmetal, H. So with that in mind, you know, well, it kind of gives it away. It says calculate the molecular weight of hydrazine. The fact it even says molecular weight instead of formula weight, you know it's a molecular compound. But hydrazine has nitrogen and hydrogen in it. So find nitrogen on the periodic table. It's definitely on that side of the jag, so it's a nonmetal. And like I said, hydrogen, consider it a nonmetal, usually for this purposes. So you have 2 nonmetals joined together, a molecular compound. So we're going to need the decimal number for nitrogen and the decimal number for hydrogen. Okay. So this actually is kind of, yeah, that works. It's the next problem I need to show explicit way. That way. So the decimal number for nitrogen is 14.01 AMUs. Remember to use units throughout your problem. So 2 times 14.01 AMUs. The decimal number for hydrogen, 1.008. 4 times 1.008 AMUs. Now notice we're both multiplying and adding, but actually since the subscripts, the 2 nitrogens and the 4 hydrogens, since that's exact, it brings no uncertainty, so it's kind of like we're adding those, 6 numbers together. So since we're adding, we round according to decimals, and we have 2 decimals in the nitrogen term, so we're allowed only 2 decimals. All right, so switching gears, calcium nitrate. Notice it says calculate the formula weight, not the molecular weight. So formula weight gives a clue it must be an ionic compound. So actually, if you find calcium in the periodic table, it's clearly a metal, so it does fall under kind of the suggestion I said. If you find a metal, it's going to be an ionic compound. So here we go. There's 1 calcium, decimal number 40.08. There are 2 nitrogens, again, decimal number 14.01. And there are 6 oxygens, the decimal number 16.00. Oxygen, sometimes I'll be grading students' work, and I'd like to say some mistakes students make, I make too, but I don't think this is one of them. Really, it's a different thing if you put 6 times 16.00 or you put 6 times 16. I mean, they're different. I know your calculator displays the same thing, but in one case, you're allowed, 4 significant figures or 2 decimals, whichever route you need to round it. In the other case, you're allowed no decimals and 2 sig figs. So I would like you to see you get in the habit of writing 16.00 for the decimal number for oxygen. So again, we go to decimals since we're basically adding all these together. There's no uncertainty in the 1, 2, or 6. So we are allowed 2 decimals, so 164.10 AMUs. Now this sort of problem, remember that periodic table I showed you on Friday? That periodic table, when it said molar mass calculator, that's kind of what it can do. Again, when you guys are doing, also, I'll just say it one more time. I'll probably say it a few more times as we go. But see where it says AMUs? You guys will probably, if you're not wanting to be old school, be using the symbol U for AMUs. So that was molecular weight, weight of a molecule, formula weight, weight of a formula unit. Now we're switching gears. It's like deja vu, back to actually Unit 1 stuff. Unit 1, we introduced the concept of a mole, 6.022 times 10 to the 23rd of something that you got a mole. And then we introduced the idea of molar mass, which is basically grams to set aside to get 1 mole of those things. And it works great for atoms, okay? If you want 1 mole of nitrogen atoms, the decimal number for nitrogen, 14.01. You weigh out 14.01 grams of nitrogen, some way, okay, and you have 1 molar mass, okay? So we're going to switch gears and kind of scale that up from atoms to molecules and formula units. Molar mass. So we said in the previous unit that the molar mass for the elements, including magnesium, molar mass for the elements is the equivalent to that decimal number, which is the average atomic weight, okay, for atoms. And here's where we get to scale it up. The few slides ago, we knocked out the molecular weight of a molecular compound and the formula weight for an ionic compound. Actually, that's those same decimal numbers, okay, are the molar masses for the compounds. Okay, and we're going to kind of use them as an important property of those compounds. So again, units of molar mass are always going to be grams of substance, whether it's atoms or molecules or formula units, grams of that thing to get 1 mole of that thing. All right, so you know it's coming, okay? Anytime you have a physical property, molar mass, density, whatever, okay, if you look at what the units are, of the piece of information you have, that actually, those units tell you what you can use it for, to go back and forth between. And we are. Okay, so here, we have 2 compounds. We have ethane, C2H6, and we have ammonium chloride. Just looking at where carbon and hydrogen is in the periodic table, carbon is clearly a nonmetal, right? And hydrogen, I said, for all intents and purposes, to identify it as being an ionic compound, consider it a nonmetal. So ethane actually is a molecular compound. Molecular CPD. Perfect. Ammonium chloride is one of those exceptions, direct. Okay, as some of you may know, okay, remember how chlorine actually picked up an electron to become what we'll call a chloride ion in sodium chloride? Well, that's what happens here. The NH4 is actually NH4 plus, okay? And so actually, yes, when NH4 plus combines with Cl minus, that forms a ... an ionic bond. Ionic bond. And here we actually have one of the exceptions for the rule I said. Because if you look at the periodic table, nitrogen is a nonmetal. Hydrogen, I said, goes nonmetal. Chlorine is a nonmetal. So you actually have 3 nonmetals. But this actually is an ionic compound. All rules were made to be broken. But our instructions for this little exercise is to calculate the molar mass, And I will say, what you're going to see is going to feel like deja vu. So basically what you're going to do for this one is calculate the molecular weight, in a sense. That's kind of how I think of it. And for this one, you're going to calculate the formula weight. You have to show all of your work to do this sort of problem. But once you have those weights, then we can just switch the units from AMUs to grams per mole if we wanted to. So this is not the way I would work this problem if I was on a roll, working it as an answer key, working it as my problem on my own. This is explicitly labeled. So in the compound C2H6, there are 2 moles of carbon, okay, and 6 moles of hydrogen. Okay, so of course this 2 is where this 2 came from, okay, or I should say this 6 is where it came from. 2 moles of carbon, 6 moles of hydrogen. We know from the periodic table the molar mass of carbon is 12.01 grams of carbon per 1 mole of carbon. And that's the decimal number for carbon. And for hydrogen, the decimal number is 1.008, so there's 1.008 grams of hydrogen in 1 mole of hydrogen. So again, this is explicit. I'm going to show you how I do it an easier way after this. But just looking at it this way, let's see what cancels. Looks like moles of carbon cancel, okay, and moles of hydrogen cancel. Okay, so we're left with grams of carbon in 1 mole of C2H6 and grams of hydrogen in 1 mole of C2H6. Of course, if we add those 2 masses together, you get the total mass, carbon and hydrogen, in 1 mole of ethane. So that's the explicit way. The easier way, which is the way I do, and I would expect you to do it, the abbreviated calculation looks like this. You find the decimal number for carbon, multiply it by 2. You find the decimal number for hydrogen, multiply it by 6. So 2 times 12.01 plus 6 times 1.008. Okay. And you round it to 2 decimals because that's what you're allowed. There's no uncertainty brought by either the 2 or the 6. Okay, but there is uncertainty in those decimal numbers on the periodic table. So actually we're kind of rounding according to decimals. So it's the same number, it's just the abbreviated way. I like this way better. This is where I run into, and I'll say it just a few times and then I'll kind of let it go, but you need to show all work. And actually, I think it seems like your homework has kind of all had that little caveat. And of course, when you work problems on your test, I'm going to say that too. Show all work. That includes this. I don't care if you have a periodic table and you just know it. Okay, show all work. All right, so let's use that abbreviated approach to knock out the molar mass of ammonium chloride. So we'll take 1 times 14.01, that's for nitrogen. We'll take 4 times 1.008, that's for hydrogen. And then we'll take 1 times 35.45, that's for chlorine. And we're going to round it according to 2 decimals. And we're going to tack on the units, since it's molar mass, of grams per mole. That's pretty easy. Sometimes you might be wondering, do I really need to put the 1s here? Okay, well, it doesn't change your answer, but to me it kind of hits you over the head that actually that 1 came from the little subscripts or implied subscripts from the formula. So it's optional. I think it's a good idea. It's a better pattern. So when it comes time for, if you have a periodic table that has like, oh my gosh, it has the atomic weights out to like 6 decimals, you know, how many decimals do you need to use? And this is kind of the rule of thumb. Okay, for the light elements that kind of cut off between beryllium and boron, okay, for just those 4 light elements, go ahead and use 3 decimals. And for everything else, use 2. So that's the general rule of thumb. 3 decimals if it's light, there's only 4 elements like that. 2 decimals otherwise. And that should get you down the road to at least having 4 significant figures when you're doing your calculations. All right, let's do a problem. So actually, don't think you have this slide. This actually is something we covered, gosh, probably was last Wednesday, where basically you were converting grams of calcium into moles of calcium. We went and got the decimal number for calcium, it's 40.08. And we recognized that for calcium, there's 40.08 grams of calcium in 1 mole of calcium, 1 mole of calcium per 40.08 grams of calcium. We could flatten it out too. Okay, and then we worked a problem. This is exactly, you guys had some homework doing this. You start with the thing you want to convert, which is grams of calcium over 1. Then we use the molar mass. I usually don't even know whether I'm multiplying or dividing. I just put down the molar mass, and I want grams to cancel, so this is the way we use the molar mass, the flipped version. We're left with units of moles and rounded to 3 significant figures. So you have that in your notes. So let's do a similar thing with a compound. So that was an element, calcium. Now we're going to scale it up to a compound. So chloroform. So the hydrogen should follow the rule. So let's see, hydrogen, a nonmetal, carbon, nonmetal, chlorine, nonmetal. Okay, so actually chloroform is a molecular compound. Remember, the thing in brackets probably won't be there in normal problems. So how many moles is 1.28 grams of chloroform? Well, in order to work this, we're going to have to knock out the molar mass of chloroform. So here it is, and I would need to see this on your paper. So the formula is C1H1Cl3. So you take 1 times 12.01 plus 1 times 1.008 plus 3 times 35.45. And we're going to have to round to 2 decimals, so that's 119.37 grams per mole. I don't think I do this in, maybe I do. Okay, but what I do, especially if I'm early on working with this, is I would unpack this. 119.37 grams of chloroform, which is CHCl3. Usually you have plenty of time per 1 mole of CHCl3. What could be more important than chemistry, right? So that's kind of what we mean by that molar mass. So let's go ahead and work the problem. The thing we want to convert is 1.28 grams. You could go ahead and put grams CHCl3. I don't think I do on my answer key, but you could. Notice we want grams to cancel, so we're going to use the flipped version of that, aren't we? 1 mole is CHCl3 over 119.37 grams of CHCl3. Notice I don't really have to put the species because I only have 1 species here. So grams cancel, we're left with moles, we're done. Bada boom. So we need to round according to 3 significant figures because that's what we have in the mass. Okay? It's all right, it's all right. Let's do one more. What mass is 0.4444 moles of methane? Actually, I know we said do one more, but I kind of want to, let's leave this for Wednesday, because then it'll give us a running start into the bromine problem. And we didn't make it to an assignment slide. We will on Wednesday. Okay? If technology works. Dang.